Welcome to the universe. We have galaxies and constellations of all shapes and sizes, black holes, some regular matter, which we call baryonic matter, lots of dark matter, which you can't see but has gravity, and also some other stuff. But mostly lots of space. Now, I imagine you have lots of questions. Well, I have answers. Well, I can tell you some answers. Best to start with the beginning of the universe, the Big Bang. Then, an early universe, seconds after, so hot and dense not even light was able to move freely, trapped between particles. Fast forward a few 3,000 years into the future, and that light finally breaks free, sending shockwaves throughout the universe in its excitement. They will later be picked up as the cosmic microwave background radiation. Fast forward again 9.6 billion years into the future, and the Sun begins to form. Soon after Earth forming, almost a billion years later, Earth life, and then, some 14 years from the Big Bang, historical Earth year 1915, we get Albert Einstein, fresh off his success with the special theory of relativity and not stopping. And so, hoping for something great, Einstein stirs for years 8, and the theory produced, well worth the wait. General relativity. It was his masterpiece and described almost everything in the universe. But how, you ask? Excellent question. Within general relativity are Einstein's perceptions of the rules and laws of the universe, the Einstein field equations. He also had this lambda thing because he thought, like a lot of other people at the time, that the universe was stable, but he removed it later because it turns out it wasn't. I'm sure it won't be important later. There are these things, which are called tensors plural, tensor singular, and each tensor has 10 components, which give us 10 equations to describe spacetime and the interactions within it. But how do those work, you ask again? Well, we can take two of them for an example. The Friedmann equations, after Alexander Friedmann. These describe the cosmic fluid, the universe so zoomed out that looking in every direction looks the same. But I'm getting there. The first equation has an A, which represents the average distance between galaxies, or the size of the universe, basically. A dot represents the speed of expansion, and together the A term, sometimes called the Hubble constant, represents the amount of energy pushing outwards in the universe, presumably from the Big Bang. The second term is called the rho term, after the Greek letter that looks like a P. It's the gravitational effect of all the matter and energy in the universe. The relationship between the two terms is pretty simple. They fight for dominance. If rho is greater, then gravity wins and the universe collapses in the big crunch. If rho is smaller, then the left-hand side goes to positive and the universe expands. Forever. If the two are equal, the universe will grow and then basically stop. On the other side is the K term, which represents the geometry of the universe, which can either be 1, 0, or -1. If K is 1, then the universe has positive curvature and looks like a hypersphere, or 4D sphere. In a hypersphere, just like on spheres, parallel lines eventually converge and the angles of triangles add up to more than 180 degrees. This is called de Sitter space, after Willem de Sitter. If K is 0, then the universe is flat, and regular geometry works fine. If K is -1, then the universe has negative curvature, parallel lines diverge, and the angles of triangles sum to less than 180 degrees. This is known as anti-de Sitter space, or ADS. Too bad it's not the standard. Anyways. The universe is expanding, left side positive, so right side should be positive, and K is 1, and the universe is finite. Except it's not. Really close to not, anyways. Remember the cosmic microwave background radiation? It also lets scientists measure the angles of very large triangles within it, and the universe should be flat. Or at least, very flat. Wait, but how do we know the universe is expanding? Well, it's thanks to these guys, who are trying to figure out the expansion history of the universe. So how do you do that? Well, take the case of a light beam from one galaxy, say A, to another, which we can call B. When galaxy A sends a light beam towards galaxy B, it becomes faded, or dimmer. Erwin Hubble was one of the notable first to see galaxies getting dimmer and thus space expanding them farther away from us. But there's more. If, when the light beam is traveling through space, the space expands, then the wavelength of that light gets expanded too. Its emission spectra, the black lines right here, go towards the red end, and so we call it redshifted. So you know that faintness gives dimness and redshift gives expansion, so to know the expansion history, all you need to find are objects whose intrinsic brightness and original spectra are known. Turns out these exist. Type 1a supernova. These are made when one of the stars in a two-star system collapses into a white dwarf roughly the size of the Earth. The younger sibling sucks away matter from its larger cousin until it reaches the mass of exactly 1.38 times the mass of the Sun and explodes. As it needs to reach such a critical mass, you can get very high accuracy measurements of brightness, and as it's a supernova, all you need to do is watch and wait. Both teams, who worked independently of each other, would publish their results in 1998, and found something that neither the scientific community nor they expected. According to their data, there was something influencing the trend line, pointing towards accelerating expansion. This something they called dark matter, won a Nobel Prize for it, and called it a decade. So it looks like there's something strange that's being added, and also something that needs to be subtracted. Clearly the solution is to add something. Okay, well, adding it to the other side is the same as subtracting. So there's something missing that needs to be added. Gee, I wonder what that could be. Let's go back and see. Aha! It's the cosmological constant, lambda. The constant part of it is dark energy's constant energy density. When placed in expanding space, regular matter and energy gets diluted away. However, dark energy remains here to stay. Its equation of state, pressure over energy density, is -1, which accounts for this. Anything multiplied or divided by 1 stays the same. But what exactly does dark energy do? Well, for that, we need to take a look at Friedman equation number 2. Taking it with regular matter, which is positive, we get negative. In essence, gravity is always attractive, and starting from stationary, the universe will collapse. Now, if you add dark energy in, we get this. Its equation of state tells us how its density is related to its pressure, so we can simplify to get this. The negatives cancel, and you get positive positive. The expansion of the universe will accelerate, and at universe year 7 billion, it will dominate the universe. Oh wait, your time is already past that. But it probably won't touch you on Earth. The gravitational force between every local cluster of galaxies is simply too strong for dark energy to ever come knocking. That is, unless its equation of state is less than 1, in which case, yeah. And those are the Friedman equations. Now you know and understand how at least 2 of the laws of the universe work, which are used by NASA in warp drive technology. Although I'm pretty sure in your time the best concept is one that can only make a round trip without stopping and no one knows how to get on and off, but it's progress. Hopefully it also showed you the importance of always asking how and why in the understanding of a topic, which can help in all sorts of ways. Come again sometime. Bye.